Hello, I'm going to do some quick examples from our lesson today, which was on Unit 3, Day 1, which was on exponential functions. Meaning, we have to understand what the parent equation looks like. Y equals some number times a base to the power of x. So because the variable, the independent variable is in the power, that's what makes this exponential. If the x were on the base part, we'd be back to our cubics and our quadratics and everything else. But because the x is now in the power, that's why we call this exponential. What you have to understand is when you're looking at these two graphs, the b, which is the base, is going to indicate a growth factor or a decay factor. So if I were to write y equals 2 to the x, there's nothing in front of the 2. That means it's just the identity of 1 in front, so there's no stretching or shrinking. But the base of 2 is a growth, and it's going to grow over each interval mark. So put in 1, what happens? Put in 2, what happens? If you look at the graph here, over 1 up 2, because we put in the power 1. We put in the power 2, we're going to go over 2 up 4. So that's just us understanding how to build a table. But what I want you to understand is the parent functions and how they look based on what's written. If the base is bigger than 1, you're going to move up to the right for your right-hand behavior. If that base changes and becomes a decimal or a fraction, and then is raised to that power, it's still exponential, but now because this factor is changed to something between 0 and 1, now when we substitute values in, everything is going to decay. Nothing will ever cross this x-axis, this y equals 0 line. They call that a horizontal asymptote, or HASI for short, because no matter what power you put into the variable, if you remember from Algebra 1 and Algebra 2 when you built your tables, no matter what power you put in, that's simply going to still keep your y values positive. Just for example, to show you, if you were to put y equals 2 to 1 in and look at the table here, you're going to get 2 out. If you were to put negative 1 in, you're going to get 1/2, because remember, negative power indicates a reciprocal. This is a good way also for us to talk about what happens when you put in 2 to the 0. Anything to the 0 power is a 1. That's why this is your parent anchor point that we always generally understand for starters, but then shift after we make some changes in our equation. So that's just a review of what does the shape of the exponential function look like, what is that parent anchor point of 0, 1 like, and remembering that the parent function has a horizontal asymptote at 0. Let's do some description of graphs that change. So all of these are given examples of giving you some reflections or some translations. I'm not going to do stretching and shrinking today, so we're just basing our information on reflections and shifts up or down. So let's see how that's going to change the parent function. Let's do right up here at the top what our usual parent looks like. Okay. All right, so let's do just a few of these. Let's try 3 and let's try 5. 3 has a base of e, so we're going to start with y equals e as my base. It's reflected over the x-axis. That means up and down movement range outside the argument negative. Shifted up 2, that's another range movement just like we just discussed. That's also outside the argument, so plus 2. The 3 to the right now is inside the argument. That means our argument is our power, so we think of opposite of what we hear, we're going to write x minus 3. So there is your equation for number 3. You just have to remember all those rules for transformations. Let's move to 5 and do the same thing in reverse. So we have our function. We know it's exponential because your variable is in your power. So what we're going to say is, okay, this type of graph that is exponential, it has a base of 3. Because of that 1 in there, it looks like we have a horizontal shift. Opposite of what we see, going to be left 1. And because of that 10 on the outside, that's going to be a vertical shift down 10. Now, what we could also do to indicate that we really understand, and excuse me, I forgot the left one. what that movement is you could say that we now understand that the anchor point that used to be 0, 1 is now going to move because of the 1 and 10 movement. So left 1, let's just put it right here, left 1 and down 10. It's going to give me a new anchor. So it's no longer an intercept anymore because it shifts, and it's going to become -1, -9. Again, 0 minus 1, 1 minus 10. So that's going to be important when we graph. The other thing that's also important is that horizontal asymptote. It used to be, remember, y equals 0, but we shifted down 10. So now the new point, passing horizontal asymptote is y equals -10. So understanding these two steps I just did really solidifies that you understand that transformation we discussed. That'll be super helpful when we graph. So again, talk about reflections and translations. Talk about your new anchor. Remember, it used to be 0, 1. It's going to change if there's anything happening up here. New direction. So parent graph usually goes up to the right. If you were to have a reflection over your x-axis, it's going to turn over and go down to the right, which means it's a new anchor at 0, -1. If it reflected over the y-axis, that means your anchor would stay the same, and it would just swing around that anchor and go in the other direction here. Again, I could draw that a little better, I apologize. Again, it would keep that anchor, but now it would hug this side and go up here. All right, so just keep that direction in mind. Sometimes it's super important to find the y-intercept. It's just for clarity to make sure we're drawing it a little bit more accurately. And remember, the parent function always has a y equals 0 horizontal asymptote, but that will change based on these reflections and translations. Let's give a graph a try. Okay, y equals -2 to the power of x plus 3. X is in the power, automatic exponential, so I immediately in my mind think of my parent graph and what it starts as a parent to look like. And now I just got to break down how that changes. We have a reflection on the outside. That means it's a reflection over the x-axis. So that means this problem here is going to now have an anchor of 0, 1, 0, -1, and head the other direction. That's going to be super important. So that changed, not only did that change direction, but it also changed our anchor to 0, -1. Keep that in mind. Looking at the rest of the problem, inside the argument you have a 3. Inside the argument, that's going to be a horizontal shift. And that's going to be left 3. That means this anchor that used to be -0, -1, because of the reflection, now is going to go left 3 on the x value. It doesn't go anywhere on the y value because there is no vertical shift. So we have a new anchor at -3, -1. Our horizontal asymptote stays the same as y equals 0 because there was no vertical shift. So let's get that back as a guideline. We're not going to cross that. Our direction, remember, goes the other way because of that reflection. So I can kind of see that it's going to be shaped a little bit like this, but go specifically through -3, -1. And let's find our y-intercept right now so that we can see what's going on right there. Y-intercept means we're literally going to take our equation and substitute 0 in for x and just finish the work. That looks like it's going to cross at -8. So now I'm going to hug the asymptote, hit that anchor, swing down through here, and now I can see that quick sweep that guarantees to me it definitely is an exponential that had a change. Those are some great examples. Please reach out if you have anything else